we present our paper Relative Pose Estimation through Affine Corrections of Monocular Depth Priors, to appear at CVPR 2025 as a highlight paper. Monocular depth estimation models, or MDE models, are evolving fast in recent years. However, their predicted depth priors are non-trivial to use in geometric tasks because of the ambiguity from the unknown scale and shifts. This is also true even for models that aim to predict metric depth. This motivates us to consider explicit modeling of the scale and shifts. On the other hand, recent 3D feedforward models like Duster or Master can also directly predict scene geometry. However, these deep learning models are great on generalizability, but lacks the geometric accuracy of classic methods, where classic methods and metrics can help. In this paper, we show that modeling both scale and shifts of monocular depth priors combined with hybrid ransack with classic methods is able to beat point-based baselines, PNP, and feed-forward models for relative pose estimation. More specifically, our contributions include 3 depth-aware solvers with explicit modeling of scale and shifts of the depth priors tailored for 3 different setup of camera pairs, 2 calibrated cameras, 2 cameras with shared unknown focal length, or 2 independent uncalibrated cameras. We call these 3 the calibrated, shared focal, and 2 focal solver in short. These solvers are combined with classic point-based solvers and epipolar constraints in hybrid estimation, which leads to consistent improvements over baselines and feed-forward models. In addition, our method is flexible to use with any feature matchers and MDE models, so you can just plug and play. In previous work that tried to utilize monocular depth priors for pose estimations, typically only a single scale is considered. In our formulation, we not only consider a relative scale between the 2 depth maps but also model 2 offsets, or shifts. Formally, given 2D pixel correspondences from some off-the-shelf feature matcher and the monocular depth maps D1 and D2 predicted by some MDE model. The goal is to estimate relative rotation R and translation T and optionally the focal lengths, by explicit modeling the relative scale alpha and shifts beta 1 and beta 2. Here is an overview of our pipeline. The 2D point matchings and the corresponding depths by looking up the predicted depth maps are fed into the core hybrid ransack module, which combines our proposed depth-aware solvers with classic point-based solvers, and uses hybrid scoring of depth-induced error together with classic epipolar error. In the hybrid ransack estimation, we randomly sample between depth-aware solver and the corresponding point-based solver as shown in this table here. The 3 depth-aware solvers each correspond to the classic 5-point relative pose solver, 6-point shared focal solver, and 7-point fundamental matrix solver, respectively. If a point-based solver is selected, we obtain the optimal scale and shift values using triangulation and least square fit. Our depth-aware solvers work in 2 steps. First, solve for the scale and shift values. Consider the lifted 3D points of the 2D correspondences, using the scale and shifted depth priors. The pairwise distance of the 3D points should be equal in both cameras' coordinate frames. These lead to a system of quadratic equations which we can solve for the scale, shifts, and optionally focal lengths. For calibrated case, the solver is minimal. Takes 3 pairs of correspondence with depth priors, solves the 3 equations and gives in maximum 4 solutions. For shared focal and 2 focal cases, the solvers take 4 pairs of correspondences, but uses only 4 or 5 from the 6 equations, and give a maximum of 8 or 4 solutions respectively. After finding the scale and shift values, the rotation and translation can be easily found by finding the rigid transformation between the lifted 3D points from both views. For scoring, we combine the 2-way depth-induced reprojection error together with the Sampson error. This is essentially treating each pair of correspondence with depth priors as effectively 3 data types, P1, P2, and D1, the depth from first view, P1, P2, D2 from the second view, and P1, P2 alone without using the depth. Note that the reprojection errors are computed in both directions. This is designed to be robust to cross-view inconsistency of the depth priors. We evaluate the relative pose estimation performance on the widely used ScanNet 1500 image pairs with calibrated cameras setting. Our method achieves best performance over classic point-based methods and previous baselines using superpoint plus light glue sparse matchings as well as Roma dense matchings, and with depth priors predicted by Moj model as well as the depth anything metric depth model. Our method improves more over the baselines in the shared focal setting, where we also compare our method with feedforward methods Duster and Master. Our method is able to improve over Master's performance significantly using the matchings found by Master, and even more if using the depth output of Master as well. We also compare on the uncalibrated or two-focal setting using about 1,000 image pairs we sampled from the Stanford 2D, 3D semantics panorama dataset with arbitrary focal lengths. The increased accuracy of our method is the most significant in uncalibrated case, as depth priors provide valuable information in this challenging setting. We also experimented on challenging image pairs with limited covisibility. As shown in the figures here, our method improves significantly over point-based baselines in these challenging low covisibility scenarios, maintaining a high accuracy and robustness. In the visualization examples here, the column of the point-based method is reconstructed by lifting ground truth depth while aligning the norm of translation of the output relative pose with ground truth pose. And the middle column of our method is reconstructed directly using the depth priors, relative pose, and scale and shifts values found by our pipeline. We can see that by using the depth priors, our method is able to recover the correct camera pose as well as the scale and shifts that align the depth maps as an auxiliary outcome, whereas classic point-based method fails to recover the pose accurately. In this visualization, we also show the qualitative comparison of our method with a scale-only ablated version that only considers the relative scale between the two depth maps without the shifts. As clearly shown here, considering only the scale leads to distortion and misalignment of the depths, and therefore hinder the estimation of accurate relative pose. Here in the ablation study, we show that modeling the shift is extremely beneficial for scale and shift invariant monocular depth models like Marigold or Mosh, but also improves the performance even with metric depth models like Depth Anything metric model. On the other hand, our hybrid estimation is beneficial for both indoor and outdoor data as it combines our depth-aware solutions and point-based methods and takes advantage from both sides. In conclusion, in this paper we show that modeling both scale and shifts of monocular depth priors enables effective use of the depth priors to improve relative pose estimation and potentially other geometric tasks. We propose to use hybrid estimation to combine depth-aware solutions with classic point-based methods, leading to consistent improvement across the three settings and different datasets. Finally, our method is flexible to use with any feature matchers and monocular depth models in a plug-and-play way. Thanks for listening. Please check out our paper for more results and discussions. The code of our solvers and estimators is open-sourced in this GitHub repo. You are welcome to give us a star if you like our work. Thanks again and look forward to seeing you at CVPR 2025.